Good morning, everyone. Today is our last lecture for midterms before we have your midterm exam this Thursday, that is January 28, 2021. So, as I have said from our previous discussion, right after our discussion for today, you will be having your first quiz for midterms, which includes our topic, which is plastic stress distribution method. Right, so other announcement regarding our subject will be given right after our discussion for today. Now let us go back to our topic here. We have here PSD, or the plastic stress distribution method, which is still in relation of what we have discussed from our previous discussion, which are composite beams. Right, so before we proceed uh, on our discussion proper, I have listed here two topic learning outcomes wherein by the end of this lecture, the students now should be able to, it says here, determine the location of the plastic neutral axis or the PNA on composite beams. What else? Compute the nominal moment capacity or the nominal moment strength now of composite beams. That is, of course, applying now your plastic stress distribution method. All right, so let us start off by defining some of the concepts under plastic stress distribution method. Now, there are two cases under the PSD method. The first one, which is case number one, it says here, the PNA or the plastic neutral axis is located now on the slab, or that is located on the concrete slab now of your composite beam. And then case number two states that the plastic neutral axis is located on the steel section now of your composite beam. Now, for you to be able to understand case number one and case number two, let us try to dive deeper now on some of the terminologies which are included on this method. So case number one and case number two will be explained much better if we are going to perform or try solving sample problems, which we are going to do later on, right after we discuss some of the terminologies which are included under this specific method. So the first one, we have here your nominal moment strength. Now it says here that the nominal moment strength, which is represented now by M sub n, we have here M sub n, is based on the plastic stress distribution system, which is now divided into two general categories, as what I have said earlier, case number one and case number two, wherein for the first one, the plastic neutral axis occurs on the slab, and then the second one, the plastic neutral axis occurs on the steel section. Now, there is a condition here. If the plastic neutral axis occurs on the steel section, what happens? It says there, the nominal moment capacity M sub n calculation now will differ depending on whether the PNA or the plastic neutral axis is in the flange or the web. So in summary, say for example, under case number two, if the plastic neutral axis is in the steel section, it can either be located now on the flange or on the web of your, say for example, I-beam. So if the PNA is located on the flange, as there will be a different solution now comparing it if the PNA is located on the web of your I-beam. Alright, let us proceed to the next statement here. It says here that the concrete is assumed to develop only compression forces. So on the concrete slab of our composite beam, it says here, it is assumed that it can only develop compressive forces. Although concrete is able to sustain a limited amount of tension, that tensile strength now is negligible since at the strains occurring when the nominal strength is reached. So the tensile strength acting on the concrete now on your composite beam is negligible, which means for the concrete part now of your composite beam, we have your compressive force And then for the steel section of your composite beam, we have your tensile force acting on that specific part of your composite beam. So, proper way of computation now for nominal strength or the equations utilized will be discussed as we try and solve examples now for regarding this method. So before we proceed to those examples, we have been talking about the plastic neutral axis. So let us try to define what is the plastic neutral axis now of a composite beam. So the first one we have here, the plastic neutral axis, it states here that it is now defined as the axis that splits the cross section in such a way that the compression force from the compression area is equal to the tension force in the tension area. All right, so I repeat, it says there, the compression force now is equal to the tension force. That is under plastic neutral axis. So say for example, let us try and talk about case number 1 first. Where in case number 1, under this method, plastic stress distribution method, it states there that your PNA now is located on the concrete slab. Say for example, take a look at this diagram. So what happens if your PNA is located now, we have here, plastic neutral axis is located on your concrete slab. Of course, you will have here your tension, this one, your tensile force now, which will represent the steel part of your composite beam. And then we have here your compressive force, which will represent the concrete part of your composite beam. Now, I will be discussing later the equations to be utilized now for the tensile and compressive part of the plastic neutral axis. Let us try to illustrate first the location now of the compressive and tensile forces regarding case number 1 here. Now, since the compressive force will represent the concrete slab here, and then the tensile force represents the steel part or the steel section now of your composite beam, what happens here now is that if I were to take summation forces horizontal, say for example here at the top, case number 1, if I were to take summation forces horizontal is equal to 0, what happens here now is that, observe at this part of the diagram, I have here the compressive force and then the tensile force. Compressive force and then the tensile force, which are directed opposite to each other. So what will happen? I will have here tensile force now is equal to the compressive force. That is for case number 1. How about, say for example, case number 2? Observe now our diagram here. As you can see, the plastic neutral axis is located now on the steel section, specifically on the flange now of our I-beam. So how are we going to represent this one? Still, the concrete part now will still be under compression, which is this one. It is still under compression. However, since the plastic neutral axis now belongs on the flange or located on the flange, we have here a small part of the flange which is also under compression. That is why I have here C sub S. And then same, the remaining part now of your I section or the I beam will belong to your tensile force here. Wherein what will happen, if I were to take summation forces horizontal, considering that diagram, I will have there the compression due to the concrete slab plus compression due to the steel area. Take note, this one, the small part above our plastic neutral axis, is equal now to the tensile force. So that is the basic concept now under case number 1 and case number 2 for this method. Now, how about if, say for example, the plastic neutral axis now is located on the web of your steel section. Say for example, at this part. So what are you going to do? Same concept. However, CS now, there, the location of your plastic neutral axis will be here at the web, wherein there will be a few alterations on our computation. However, still the same concept as having the plastic neutral axis on the flange here. So we will be discussing that as we proceed on a sample problem under case number 2. Okay, so let us proceed to the next one. Our next slide here, I have here plastic stress distribution method equations. So as I've said, we have here your equations now for the compressive force and then your tensile force. Now when we talk about your compressive force, that is just the area now of your concrete, multiply it by Fc prime. However, how are we going to represent AC or A sub C here? A sub C now is represented by, we have here your 0.85, multiply that by A, multiply it by B. Wherein A here now is, it says here, the location of the PNA from the topmost part now of your composite beam. Let us try and represent this one later on. And then how about B? B now is the width of your concrete slab. I repeat, B there is the width of your concrete slab. Of course, Fc prime, that is your 28-day compressive strength of concrete. However, where did we derive this equation? 0.85 A times B for the area of your concrete. Take note if you are going to recall your RC1, reinforced concrete 1. So that is from your 2001 NSCP or the National Structural Code of the Philippines, wherein this one belongs now under the provision for singly reinforced beams. So that is your SRB, singly reinforced beams. So this equation now is derived from that provision. So for our compressive force, therefore, we will have an equation which is equal to, I have here 0.85 A times B times Fc prime. So we will be utilizing now this equation for the compressive force under this method. How about the tensile force? For the tensile force, that is simply the area now of your steel section, multiply it by Fy, wherein Fy here is yield strength of the concrete. Yield strength of concrete. So why did I include here A? Why did I include here A wherein we do not have A on this equation? That is because if we are going to equate now compression is equal to the tensile force, we will be able to determine now the value for A, wherein that is what we are trying to do for us to be able to determine now your nominal moment capacity. For us to be able to determine first the location of your plastic neutral axis. Because the location now of your plastic neutral axis there, the location of your plastic neutral axis is very crucial now if you are trying to determine the nominal moment capacity or the nominal moment strength now of your composite beam. Alright, so other equations now will be introduced as we go on through our discussion. So these are just two of the basic equations. We have your equation for your compressive strength and then equation for your tensile strength. Right, so let us proceed with an example which belongs now under case number 1. Now, since this is case number 1, we already know that the plastic neutral axis belongs now or is located on the concrete slab. However, let us try and solve and show how are we going to determine now the location of the PNA Then at the same time, according to the problem, determine the nominal moment capacity of the given composite beam, of course utilizing plastic stress distribution method. So I have here a composite beam having Fc prime which is equal to 28 megapascal and Fy which is equal to 250 megapascal. Dimension now of our concrete slab, that is 1,500 millimeter by 150 mm, wherein our steel section here has a flange of 305.80 millimeter and a thickness of 17 mm, that is for the flange, and then a web thickness of 10.90 mm, 10.90 mm. So let us try and determine now the nominal moment capacity of this steel or composite beam. All right. So say for example, let us utilize this diagram. Now I have already placed here some lines for us to be able to draw now later on when we have already determined the location of the plastic neutral axis. So the first step always, that is now to locate the location of your PNA. So let me write here. The first step, that is now to locate the location of your plastic neutral axis. Wherein how are you going to do that? We are going to equate now tension is equal to the compression. Wherein take note, why did I equate this one? That is because according now to what we have read earlier or what we have discussed earlier, it says there, for a composite beam, we are going to assume now that the compressive force on the compressive area is equal to the tensile force on the tensile area. So let us substitute the equation for tensile and then compressive force here. I have here the area now of your steel section, multiply that by Fy is equal to 0.85 A times B Fc prime. So let us isolate A here. So divide both sides by 0.85 B Fc prime. So I will have there A, which is equal to AS Fy, divide this by 0.85 B Fc prime. Wherein, do we know the value of these quantities? So we already know the value for B, which is 1,500 millimeters. The value for Fc prime, that is, let us go back to the problem, 28 megapascal, that is equal to 28 megapascal. Fy is equal to, that is 250 megapascal. And then the last one, AS. I need the value for AS. That is just area of our steel section. So let us determine the area of our steel section. That is, let us start with the flange. 2 multiply that to 17 times 305.80 plus area of the web, that is now thickness 10.90, multiply that by we have here 311.20 minus 17 times 2. I have here 277.20. 277.20. Therefore, the area now of our steel section is equal to, input that on your calculators, and then 10.90 times 277.20, I will have here 13,418.68 millimeter squared. So substitute that one on our equation. So we will have here the value for A now, which is equal to 13,418 28.68, multiply this by Fy, which is 250 megapascal, divide this by, I will have here 0.85 times B, which is 1,500 millimeters, multiply it by Fc prime, which is 28 megapascal. A now is equal to 13418.68, multiply that by 250 megapascal times 0.85 times 1,500 times 28, I will have there 93.97. I have here 93.97 millimeters. Now, as we have said earlier, it says here, A now is the location of the plastic neutral axis from the topmost part now of your composite beam. Now take a good look at the value now for A. A now is less than the thickness of our concrete slab. So A here is less than the thickness of our concrete slab, which is equal to 150 mm, which means that P and A now, or our plastic neutral axis, is located on the concrete slab. So we now know the location of our plastic neutral axis, wherein the location of our plastic neutral axis is here on our concrete slab, which is 93.97 from the topmost part now of our composite beam. Another way to check if, say for example, our computation here is correct, that is now by determining and then comparing the strength of the concrete by the strength of the steel. How are we going to do that? Let me write it here. Another way, that is to compare the strength now. Compare the strength of concrete with the strength of steel. So, how are we going to compare the strength of the concrete by the strength of the steel? Strength of concrete is denoted by the equation. Let us write here. Strength of concrete is equal to the area of the concrete times the 28-day compressive strength now of your concrete. But this time, instead of utilizing now the provision from your NSCP 2001, area of concrete here simply means the base times the thickness now, or the width times the thickness of the concrete slab. So I will have here 1,500, multiply this by 150 times 28. Strength of concrete now is equal to 1,500 times 150 times 28. That is now 6.3 times 10 raised to 1, 2, 3, 4, 5, 6. 4, 5, 6. So that is 6.3 times 10 raised to 6. This is now in Newton. That is the strength of the concrete itself. So what's next? Compare it with, dito na lang, the strength of the steel section. So if we are going to compute the strength of the steel, that is just the area of the steel times Fy. Wherein, what is the area of the steel? I have it here. That is now 13,418.68 millimeters squared, multiply that by 250, I will have here now, sorry, this is, I have here, oh, it cannot, dito na lang sa baba, multiply it by 250, our answer here now is equal to 13418.68 times 250. That is 3.35. I will have here 3.35 times 10 raised to 6. 3.35 times 10 raised to 6 Newton. Wherein observe now that the of concrete strength of concrete is greater than the strength of steel. Now, since the strength of concrete is greater than the strength of steel, that means that the plastic neutral axis now belongs on the concrete slab of our composite beam. However, if the strength of the steel is greater than the strength of the concrete, the plastic neutral axis will therefore belong on the steel section of our composite beam. All right, let us continue with our computation. Now, since it says there, the location of our plastic neutral axis is on the concrete part, so I have it here. So say for example, this is now our plastic neutral axis. So how are we going to represent this one? So say for example, the top part now, this is now our plastic neutral, this part now is our plastic neutral axis. Wherein if I were to represent this part, dito na lang, the plastic neutral axis. Wherein if we are going to represent our diagram, or if we are going to create our diagram for us to be able to determine now our nominal moment capacity. So say for example, for our compressive force, let us draw it at this part. So we will be having our compressive force here, which is now directed this way. Then at the same time, I will have here our tensile force. So our tensile force now is directed this way. So we will have here our tensile force. All right, so there. Our compressive force now, let us denote it here as C sub C, which is the compressive force due to the concrete. And then this part now is the tensile force due to the steel section. So take note that this distance now, this part, this distance, the value here now is A. Now since this part or this area is the location of your plastic neutral axis, wherein A now is the location of your plastic neutral axis from the topmost part of our composite beam. Now how am I going to determine now the value of our nominal moment capacity? So number 2 here, our second step, determine M sub n. So for me to be able to determine M sub n, that is either I take summation of moments here at the tensile force. So if I were to take moments here at the tensile force, what will happen? The tensile force here will not rotate. However, C sub C here now will rotate, right? C sub C here will rotate. Wherein C sub C, that is your compressive force due to concrete. Or I can also take moments here at C sub C, wherein our compressive force now will not rotate, and then tensile force here will rotate about the compressive force, location of the compressive force. Now for us to be able to do that, I need the distance, the vertical distance from the compressive force to the tensile force here. Take note that the tensile force and then the compressive force is always at the center now. See, for example, tensile force, it is now at the center of the I section, and then the compressive force is at the center now of A here. So if I were to determine the vertical distance, let us name this y. How are we going to do that? So that is just equal to, say for example here, y now is equal to the total distance 311.20 plus 150, that is 311.20 plus 150, 461, 461.20. Subtract that by 461.20, subtract that by, that is 311.20 all over 2, which is this distance. Then what else? Subtract it by half of A, right? So I will have here minus 93.97 all over 2. Now substituting those values on your calculator, I will now have a value for y, which is now equal to 258.62 millimeters. So we now have a value for y which is equal to 258.62 millimeter. Now, as I have said, for us to be able to determine the nominal moment capacity, either we take moments at T or we take moments at C. Either way will give us a or the same answer. So say for example, if I were to take moments at T, what will happen? Force T will not rotate and then C will rotate about T. Therefore, I will have here M sub N now is equal to C sub C, multiply that by Y. Or the same, I will have here, taking moments at C, C sub C, or the compression force will not rotate, wherein the tensile force will rotate about C sub C, wherein I will have here T, which is equal to multiplied by Y. So let us utilize this one. So M sub N now is equal to, I will have there 0.85, multiply it by the area now. What is A? The value for A is 93.97, multiply it by B, which is 1,500, times FC prime, which is equal to, that is now 28 megapascal, multiply it by Y, wherein what is the value of Y? That is 258.62 millimeter. Wherein our nominal moment capacity now is equal to, we will have there 93.97 times 1,500 times 28 times 258.62 divided by 1,000. That is now 867, or that is 867,600,014. This is now Newton millimeter. For simplifying this one, M sub N is 867 867.60 kilonewton meter. This is now our final answer. The nominal moment capacity of our composite beam. So say for example, if we are going to try T multiply it by Y, that is just the area now of our steel, which is equal to 13418.68 multiply it by f sub y, which is 250 times y, which is 258.62. That will give me 867.58 kilonewton meter. So very close with this one. So I have here 867.60 kilonewton meter as our final answer for case number 1, which is the plastic neutral axis located on the concrete slab of our composite beam. All right, so that is it for case number 1. How about case number 2? All right, so we have here case number 2, sample problem. So it says here, with the same steel section or with the same composite beam, determine now the nominal moment capacity of the given composite beam using plastic stress distribution method. So same composite beam, however, we have here a different 28-day compressive strength for concrete and then different yield strength or yield stress now for steel. Fc prime now is equal to 21 megapascal, then Fy is equal to 415 megapascal. Now, will there be a difference under the location now of our plastic neutral axis? So let us try and solve this problem. Now, same composite beam, however, different values for Fc prime and Fy. So the first one is for us to determine now the location of your plastic neutral axis. So let us start here. First step, locate now the plastic neutral axis. So same as what we have done under case number 1, tensile force is equal to the compressive force, wherein tensile, that is ASFY, is equal to 0.85 A times B FC prime, wherein A now is equal to ASFY all over 0.85 BFC prime. So let us try to write all of the given, where I have here B, which is equal to 1,500 millimeters, Fy is equal to 415 megapascal, Fc prime is equal to 21 megapascal, and then we have As as what we have computed earlier. So let us try to write it here again. That is now 2 times 17 times 305.80 plus, that is now 10.90, multiply it by 277.20. AS now, or area of our steel section, is 13418.68. So from there, substitute it on our equation, then we will have A, which is equal to 13,418.68, multiply it by 415 megapascal, divided by 0.85, multiply that by B, which is 1,500, times Fc prime, which is 21. The value for A here now is equal to 13,418.68 times 415 all over 0.85 times 1,500 times 21, that is now 207.98 millimeters. That is now 207.98 mm. So what will happen now here? A here is greater than, A now here is greater than the thickness of our concrete, which is equal to 150 mm. Therefore, our assumption here now is that the plastic neutral axis is on the steel section. Now, comparing it with what we have done under case number 1, when we were able to determine that A is less than the thickness of our concrete, we immediately assumed that the location of our plastic neutral axis is the distance now, which is denoted by A itself. However, for case number 2, that is not the case. I repeat, for case number 2, we cannot assume immediately that A here, which is 207.98, is the vertical distance from the topmost part now of our composite beam as the location of our plastic neutral axis. That is because we still need to test whether, say for example, if our plastic neutral axis belongs now on the flange or on the web of our steel section. And how are we going to do that? The first step is to assume a location now for your plastic neutral axis. Say for example, let us assume that the location of our plastic neutral axis is here at the bottom now of the flange of our I section. So that is just an assumption, as an assumed location of our PNA. So from there, let us now proceed with our computation. But before we proceed there, for this one, how are you going to check if this is correct? Our computation here is correct. You can solve again for the strength of the steel and then strength of the concrete, and then compare if the strength of the concrete is less than the strength of the steel. Therefore, our computation here now is correct. Right. Going back with what we have done here, now since we assume that the location of PNA is here on the flange, let us try to determine if our assumption is correct. And how are we going to do that? I will have here, let us draw our diagram first. Say for example, this is now our compression force. So I will have here this part now, which are in compression, and then this part in tension. This part of our composite beam in tension. Alright, so I will have here the tension now caused by the web and then the bottom flange. And then at this part, now since we assume that the location of our PNA is in the flange, what will happen? I will have here compression due to the concrete and then compression due to the steel itself. So from there, what are we going to do? We are going to determine the value of the compressive force and then the value of the tensile force. And we are going to compare the two. Say for example, let us try and determine first the compressive force. Let us denote that as A. We have here your compressive force. Wherein for our compressive force, that is C, that is now a combination or the sum between the compressive force due to concrete plus the compressive force due to the steel itself. So from there, C now is equal to This is concrete, so I will have there 0.85 A, which is equal to 150 mm. Take note, why did I not consider the value of A here? That is because I am trying to determine now the compressive force due to the concrete, which is now based here on our drawing, which is 150 mm. And then, as I have said earlier, A here now, under case number 2, will not automatically, A here now will not automatically determine the location of our plastic neutral axis. That is for case number 2. But if you are dealing with case number 1, wherein the plastic neutral axis is located on the concrete beam or concrete slab, therefore, A here, A now will automatically denote the location of your plastic neutral axis. Right? So continuing with our solution, that is A times B, which is 1,500 millimeter, multiply it by Fc prime, which is equal to 21 megapascal, and then add that one to, sorry, that should be plus, add that one to the compressive force now caused by the topmost flange now of our steel section. So that is just area, since that is a rectangular area, that is 17 times 305.80, multiply it by Fy, which is equal to 415 megapascal. Compressive force now is equal to 0.85 times 150 times 1,500 times 21 plus 17 times 305.80 times 415. I will now have here 6.17 times 10 raised to 6 Newton. So I will have here 6.17 times 10 raised to 6 Newton. Alright, that is for the compressive force. Compare that one with the tensile force here. Letter B for our tensile force. T now is equal to the area of the steel, remaining steel, times Fy. T now is equal to 17 times, that is 305.80, plus, I will have here 10.90, multiply it by, that is now 277.20, wherein this quantity is to be multiplied with F sub y, which is equal to 415 megapascal. Tension now is equal to 17 times 305.80 plus 10.90 times 277.20 times 415. I will have there 3.41 Newton. 3.41 times 10 raised to 6 Newton. Now compare now the value for the compressive force, which is this one, and then the tensile force, which is this one. The compressive force now is greater than the tensile force, which means that the plastic neutral axis now is located on the flange. So our assumption now is correct. So if, say for example, tensile force now is greater than the compressive force, our assumption now is incorrect. Therefore, our plastic neutral axis now belongs on the web of our steel section. But since our compressive force here is greater than the tensile force, what are we going to do now? The plastic neutral axis now is located on the flange. Now our next problem is, at what distance now from the topmost part of the flange is the plastic neutral axis located? That is because we cannot assume immediately that the plastic neutral axis is located at the bottom of the flange. So we need an exact number as to which the location of the plastic neutral axis here on the flange itself. So let us continue our computation. Okay, so now that we are sure that the plastic neutral axis is in the topmost flange of our steel section, we now need to determine at what part now of that flange is the plastic neutral axis located. So at what distance? So say for example, let us place it there. And then I will denote this part now as this one. Let us denote this part as your y sub 1. So if we are going to draw now our diagram, what will happen? I will have here our compression part. This is now our compression diagram, wherein we will have here compression due to concrete, and then at this small part, we will have here compression due to steel. And then at this part of our diagram, this one, we will have here now your tensile stress due to the steel section. So we have here your tensile stress. Now, we need to determine the value of y sub 1. And how are we going to do that? That is, of course, by equating summation forces horizontal now is equal to 0. So what will happen? I will have here C sub C plus C sub S now is equal to our tensile force. As usual, C sub C here now will provide 0.85 times A. This time, I will utilize here 150 mm times 1,500, which is B, times FC prime, which is 21. Plus, for CS, our equation here is ASFY, since we are dealing with a steel section, wherein AS now is equal to, I will have here our base, which is equal to 305.80, but our thickness, let us denote that one as y sub 1. Then what else? Multiply this by Fy, which is 415. Now, we already know our value for C sub C plus C sub S. Equate this one to our tensile force here. Wherein for our tensile force, that is now equal to, let us start with the top. I will have here 305.80. Multiply it by the remaining distance, wherein what is the remaining distance? That is now 17 minus y sub 1 times Fy, which is 415. What else? I will have there 10.90. Multiply it by 277.20. Now, where did I get 277.20? That is 311.20 minus 17 times 2. Multiply this by 415. And then the last one, the bottom flange of our steel section, that is now 305.80 times 17. Multiply it by 415. Input this on your calculator. We have here one unknown, which is y sub 1 there, and then y sub 1 here. Therefore, the value now for y sub 1 is equal to, input that on your calculators, I will have here 6.12 mm. I will have here 6.12 mm. Now let us check if it is correct. So I will have there 0.85 times 150 times 1,500 times 21 plus 305.80 times y sub 1 times 415, equate that to 305.80 multiply it by 17 minus y sub 1 times 415 plus 10.90 times 277.20 times 415, then the last one, 305.80 times 17 times 415. The value now for y is 6.12 mm. So we now know the value for y, which is 6.12 mm, wherein what is the remaining value? 17 minus y sub 1 will therefore be 17 minus 6.12, that is 10.88 millimeters. 10.88 millimeters. Now this part from your plastic neutral axis to here is 10.88. Now y1 is the location now of your plastic neutral axis. That is from the top flange going down, which measures 6.12 mm. So we are now ready to determine the nominal moment capacity. However, if I were to take moments at t, c sub c and c sub s will rotate, which means I will have to determine the vertical distance of c sub c and then c sub s from t. So for me to be able to do that, I have to determine first the vertical distance, say for example, of t to the bottom flange. Let us name this one as y sub 2. And then the vertical distance here up until here at t, from c sub c to t, let us name this as y sub 3. And then from c sub s up until c sub s up until the tensile force, let us name that as y sub 4. So for the first one, if I were to determine the value for y sub 3 and y sub 4, which I will be utilizing to determine the nominal moment capacity, I have to determine y sub 2. Since the location now of the tensile force here is not in the centroid, or it's not at the center of 311.20. That is because our plastic neutral axis now is not located within the concrete slab. So how will I determine y sub 2 here? I can utilize Varignon's theorem. So utilizing Varignon's theorem, let us determine the value of y sub 2. So the value of y sub 2, that is area total, multiply that by y sub 2, multiply that by AI times yi. Of course, area of each part times its distance from the bottom part of our composite beam. So our area total, if I were to start at the bottom, I will have there 17 times 305.80 plus what's next, that is 10.90 times 277.20 plus the other one, that is 305.80, multiply that by the remaining I have here 10.88, wherein this quantity is to be multiplied by y sub 2. Equate this one to each area. I will start here at the bottom part. So I will have here 17 times 305.80, multiply this by its distance, which is 17 all over 2. Next, I will have there 10.90, multiply that by 277.20. The distance from its centroid to the bottom part now of our composite beam So I will have there 277.20 divided by 2 plus 17 mm. I will have here 155.6. And then the last one, the topmost part, I will have there 10.88, multiply it by 305.80 times its distance, that is now 17 plus 277.20 plus, that is 10.88 divided by 2. I will have here 299, 80, 299.64. Let us simplify this one. Our total area now is 17 times 305.80 plus 10.90 times 277.20 plus 305.80 times 10.88. I will have here 11,547.184 y sub 2 is equal to, if I were to simplify this one, I will have here 17 times 305.80 times 17 all over 2 plus 10.90 times 277.20 times 155.60 plus 10.88 times 305.80 times 299.64. I will have here, I will have there 151,130.746. Divide both sides by 11,547.184. Y sub 2 now will therefore be 11,547.184. I have here 130.87 millimeters. So I have here 130.87 millimeter, which is now the value for y sub 2. 130, this is 30, let me rewrite it. This is now 130.87 mm. Now let us determine the value for y sub 3. Y sub 3 now will therefore be, the total length is 311.20 plus 150, that is equal to 461, 461.20. Let us change. So y sub 3 is equal to 461.20. So y sub 3 is equal to 461.20. That is of course minus, this is at the center of C sub C, so I will have here 150 all over 2 minus y sub 2, which is equal to 130.87 millimeters. Therefore, the value for y sub 3 now is equal to 461.20 minus 150 all over 2 minus 130.87. I will have here 255.33 mm. And then the last one, y sub 4 is equal to 461.20, that is now minus 150 minus half of y sub 1, which is equal to 6.12 divided by 2, and then minus y sub 2, which is 130.87. Y sub 4 now is equal to 461.20 minus 150 minus 6.12 all over 2 minus 130.87. That is now 177.27 millimeters. Right? 177.27 millimeters. So we can now determine the value of our nominal moment capacity. So for step number 2, solve for m sub n. Wherein, for m sub n, if I were to take moments at t, or the location of our tensile force, therefore, I will have c sub c multiplied that by y sub 3 plus c sub s multiplied that by y sub 4. Our nominal moment capacity will therefore be, what is the value of c sub c? That is 0.85 times 150 times 1,500 times fc prime, which is 21, times y sub 3, which is 255.33, plus c sub s now is equal to, take note that c sub s is still area of c sub s is equal to, I will have there 305.80 times 6.12 times Fy, which is 415, times y sub 4, 177 point, that is now 27. Our nominal moment capacity will therefore be 0.85 times 150 times 1,500 times 21 times 255.33 plus 305.80 times 6.12 times 415 times 177.27. We will have here 1, 2, 3, 4, 5, 6, 1163, 1163, 149, 149, 552, 552 Newton millimeter, or that is 1163.15 kilonewton meter, which is now our final answer for case number 2 sample problem. So that is 11631.15 kilonewton meter. So let me change this one. This is supposed to be 150. So that is case number 2 now for plastic stress distribution method. Okay, so the question here now is, how about if our plastic neutral axis is located on the web? How are you going to determine that one? That is, the plastic neutral axis is located on the web if tension now, or the tensile force, is greater than the compressive force. So if that's the case, how are you going to compute now for your Mn? What will happen? Instead of having your plastic neutral axis here, place it here, wherein what will happen, the computation now for your CS, you will have to denote this one, this whole part now as y sub 1, or that is 17 plus y sub 1, since your plastic neutral axis is here on the web. So what I'm saying is that kung andito yung plastic neutral axis nyo, if your plastic neutral axis is located on the web, how are you going to compute now? Of course, you need to determine the location of y sub 1. And how are you going to do that? You already know the thickness of your flange. So how are you going to determine now this part That is 17 plus, if you're going to denote this one as y sub 1. Then from there, same concept, determine the distances now of the location of your tensile force, the location of C sub C, C sub S. For your C sub S, you can create two. Kapag yung location ng plastic neutral axis nyo is here on the web, you can create two C sub S. The first C sub S will denote here for the flange, and then the second C sub S will be here for the web. Okay? So that is all now for case number 2 under PSD method. Okay. So as I've said, if you have any other questions regarding our discussion for today, feel free to image me on our Canvas or on my Outlook email. We have uc-bcf. On my Outlook email, which is rdbolide@uc-bcf.edu.ph. Now, I repeat, for your exam, the topics included now for your midterm exam will be from plastic design up until what we have discussed today, which have your PSD method. Kindly review your notes, review everything, wherein your exam now will start from 7:30 in the morning, and then it will end by the end now of our schedule, that is 10:10 a.m. Of course, the problems given now will be proportionate with the available time. Now, if there are any problems regarding your internet connection on your date of exam, kindly inform me. Say for example, you have power interruption on that day, kindly inform me, or anything that might happen which will hinder now you taking the midterm exam. All you have to do is to inform me. Then of course, I will have to create another set of exam for you. You will not be taking the same exam as what I will be giving this week, which is Thursday. Now, for your CS class, let us recall, we have plate 101, which was given by Engineer Garwageo, plate 102, and then your seat work. Now, there are still some of you who are unable to submit plate number 101 and 102. I would like those students who are unable to submit their plates to please submit it. I still accept late submission now of activities. However, there will be deductions now on your part. Of course, the seat work, however, you can still submit your seat work if you are unable to submit it on the said deadline. However, again, deductions now will be given on your output. All right, regarding your quiz, kindly go to your Canvas accounts. Your quiz now is placed on your Canvas accounts, which will be available right after our discussion up until 12 o'clock midnight today. So please submit your activities so that you will have a passing grade now for this subject. So if you want to have a passing grade for this subject, please review what we have discussed, starting from plastic design up until what we have discussed today. We have your PSD method. So that's it. Thank you very much. And then good luck on your quiz, good luck on your exam, and have a great day.